Hello, everyone. Good evening. My name is Chris Wade, and today I'm going to be talking about how you turn electronics into other electronics in order to make them do something nefarious. So a lot of us know about these particular devices. We have the Geltec IMMe, a device that was converted into a spectrum analyzer using the RF chip inside, the Titera MD380, which had their firmware modified to get a promiscuous mode on the frequencies, and the Artel SDR, which used a debug mode on it in order to get full access to the frequency range that it could support. Now, all these things have different cool features that were put in by someone else via reverse engineering. But for my project, I decided to do something different. I decided to decide on the features I wanted in the first place and then build a device based on something that I found arbitrarily in order to do it. So what I first did was decide on the desired functionality, assess the available features I wanted, and identify if I could find something that could be debugged and developed for this purpose. What I wanted was an LCD screen, a menu button, USB device communication, and onboard storage, so that I could make a device capable of emulating USB devices, such as USB disks, USB keyboards, or anything else I wanted. And I ended up looking around and finding this particular device. Now, this is an OBD2 reader. That's an onboard diagnostics tool for debugging CAN systems in cars. Which I found had just quite a good form factor for exactly what I wanted. It had a nice screen, some buttons, and USB connectivity. It utilizes an STM32F103 MCU, which is a very common microcontroller, which has 64 kilobytes of flash and 20 kilobytes of RAM, which is plenty for what I wanted to do as well. It's capable of going up to 72 megahertz in maximum clock speed, and had an LCD screen, nice USB interface, CAN interface, and menu buttons, as well as 8 megabytes of additional storage on the board. First thing I wanted to do is make sure that it had proper USB functionality. Now, we'll come into this later, but one of the biggest problems you have when you work with USB is people putting serial USB on their board rather than letting native USB be used. So what I ended up doing was downloading the firmware update tool specifically for the device, going through the DLLs and finding the DLLs which basically directly related to STM32 CDC communication or any STM32 communication it could via USB. This would basically let me know that it's using true USB rather than using just a serial chip where I'd use something like COM0, COM10, etc. First thing I want to do is see if I could find an SWD header on the board. This would allow me to easily delete the code off the device and debug it. I found that SWD was disabled, even though a header was there, and it had readout protection enabled, which meant even if I'd got SWD access, I would not have been able to read the flash off it. I also found, after downloading the firmware payload using the firmware update tool, that it was encrypted, so there wasn't much I could do with there at that point. So I had two options. I could either build the firmware from scratch by deleting everything off the device or breaking the readout protection. In the end, I decided to do both, but I decided to go for the first one first. So building it from scratch would mean I wouldn't have to adhere to their firmware update utilities, wouldn't have to be limited by the amount of flash access they had, and I would have to do a bit more hardware reverse engineering than I would have to do if I had the firmware in the first place. But having the firmware would allow me to modify existing software on it to make it do something else, but would require me to find some exploitable weaknesses that would allow me to break that encryption on the device. So most STM32s, which have readout protection enabled, can just have their firmware deleted. This is the same for most chips that you work with. If it says that the chip flash is locked, you can tell it to delete all the flash off it because there's nothing on there you want anymore. Logic analysis of all the peripherals on the device can let you know what the protocols are doing on any devices you don't understand. In this case, it was the LCD screen. And you can trace every single pin in order to find out what it does. I decided to just solder an SWD header out the side of the board just to make it easier for me to program. So on the board, we have several chips and ICs, etc., to work with. First is the STM32. Now, this is the core of the device. It's the microcontroller. It does everything, has the firmware and everything. We then have the SPI flash, which is an 8 megabyte flash chip, which had all the data for the OBD2 diagnostics. We had a ribbon connector for the LCD screen on the board. We had a bunch of regulators and CAN interfaces for the CAN communication, and a connector for the CAN bus, which I ended up taking off because I didn't need it. We also had some buttons, which were obviously simple. I ended up tracing out every pin and its function and mapping out in the STM32 cube. Now, this is a piece of software which lets you define peripherals and libraries for every pin on a device in order to build a piece of software without having to know too much about registers or how things work. From this, I could get basically interrupts for buttons, USB communication, SWD communication, SPI communication, and the data bus for the LCD, which came into play later. So let's talk about the peripherals a bit. First, we had SPI flash. Now, all SPI flash uses a very common command set with deletion, reading, etc., which are used to basically read and write data from the device. This STM32Cube had built-in USB libraries, basically for the mass storage and keyboard interface I wanted for the device. And the LCD screen had a part number, but no data sheets whatsoever, which wasn't too helpful. There are also pinouts for this LCD screen in sales documents and things, which came into play later, but didn't give you much insight on the exact protocol. So we'll start with the LCD screen. This is the pinout I found, which basically defined what certain pins do when they're high and low, which basically let me know that the thing was running in a parallel mode with a very specific command set. Because of this, I could trace all the pins and set them to inputs and outputs as needed in order to start fuzzing on that interface. So I realized that it was using 8 GPIO pins in order to read and write data from the memory of the chip in the LCD controller. And from that, I could start following different standards for the controls in order to get where I wanted to go. And by doing this, I eventually got the thing to turn on, which basically meant that I could see snow on the screen because it had no memory that had been initialized yet, but eventually allowed me to start printing out ASCII bitmaps onto the screen using the row and column interface that it had. I then eventually made it have a skull on the screen because it looks cool, which was an extremely difficult thing to do. Because these kinds of screens have basically rows and columns, as you would find in a text terminal, it can be difficult to draw graphics on. But if you put enough time in, then you can do, which obviously was totally worth it. USB devices are much simpler on the STM32Cube. Now, this is a huge stack to work with usually, but if you use the libraries they have built in, and spoilers, every single developer who uses these chips uses these libraries for it, you can basically make any standard device you want. It has ones for HID, which would be mouse and keyboard, mass storage, or anything else. I used these libraries, which had special functionality to let you read and write to different peripherals, and paired it with the SPI flash, basically taking the read and write functions of the flash in order to match them together, allowing me to basically use the device as an 8 megabyte USB hard disk. I then added the LCD screen to let the files, let you select files from it in order to run certain payloads. So this SPI flash has enough room for a normal FAT32 file system because it had 8 megabytes of storage, which is almost as much as the floppy disk, or just a bit more, I think. I implemented the read and write commands from the USB and mapped them to flash read, erase, and write commands, and modified the USB maximum block sizes to match those minimum block sizes of the SPI flash, which is at minimum 4K. I then utilized the FATFS library system, which lets you handle FAT32 storage on an embedded device together in order to read and write SPI commands when it was in keyboard mode. So I mounted it as a mass storage device, added some text files to it, and let them print out on the screen, depending on what mode it was on. And what this allowed me to do was step through and run payloads that are embedded in these text files. So I made the thing mount as a USB keyboard by setting up the USB HID descriptors, and made it read through the text files by converting the ASCII text in there to USB scan codes, which are used by keyboards in order to define which buttons you'd pressed. This allowed me to allow for automatic typing of a text file, much like a Bash Bunny or a USB rubber ducky. I made a few shortcuts on this in order to get the thing working before this conference. I made sure that when I plugged the thing in, it was either a USB disk or USB mass storage, because making it not be anything when you plug it in is quite a complex task and can crash your USB controller, as I found during testing. SPI Flash, USB, and FATFS were all made to match their right block sizes, so they all work together very succinctly. And I made it so you could only select text files on the disk. Now, there's a quick demo of me plugging this device in. So, obviously, in disk mode, it comes up with a skull. And then plug it in again, and you have a list of the files that are in there. Now, you could select these files, and they would type on your screen. So you could add in reverse shells or usual payloads or anything you like. Now, I talked about breaking the firmware earlier, and we're going to go through that now. The firmware update was encrypted. Now, it wasn't signed or anything complicated. It was just encrypted, which is a difficult task. And because code readout protection was enabled, I just couldn't read it from the disk via SWD. And no known generic attacks, such as cold bootstepping, were viable in this case because it didn't read the firmware when it was executing it after deployment. So a few opportunities we had were the fact that this particular chip was vulnerable to glitching attacks, but I decided not to go down that route because it's slightly too frustrating to do. But SWD is enabled in firmware upgrade mode, which meant I could read the RAM when the thing was doing a firmware update, meaning I could read exactly what's going on and crash the device as I was deploying firmware to it. The update tool functions over USB, which is easy to emulate using libUSB and different tools like that. And updates were decrypted and flashed directly to the chip with no signing or CRC, so I could upload a corrupted firmware to the device without crashing it or causing any problems. So I use the USB proxy tool for the BeagleBone Black, which is an extremely effective USB proxying mechanism, which allows you to basically actively man-in-the-middle USB connections between a host and a device, even without control of the host, and identified the CDC communication with a CRC16 going on. Now, I could then just replay these requests as needed. I took the payloads I had and wrote a tool in libUSB to emulate exactly what the host was doing. I replayed each individual packet that was used for the firmware updates and assessed where I needed to, the bits that I needed to modify in order to start uploading malicious firmware. I found the firmware was set in 512-byte blocks, which was very important later. So here's some of my code. I know it's amazingly well written, but what I tend to do when it comes to these sorts of deployments is copy and paste large buffers from the man-in-the-middle sections and just dump them in, because they're exactly as effective as me spending way too much time working out what each of these parts do. I only need to modify the parts which are necessary for what the exploitation I want to do. So I basically took the part where it was uploading firmware, put in my own part by reading it from my manipulated file, and made sure the CRCs matched. Now, I was using a very standard X.25 CRC, which is used in all sorts of networking protocols, and together allowed me to upload the firmware. This would be corrupted firmware because it was still encrypted in ways that I didn't understand. But because I could read RAM off the device as I was going along, I could find 512 bytes of the firmware at a time and read it from the device in order to very, very slowly read the firmware from it. This would let me know where the payload was in RAM, allow me to do some further attacks later, but wouldn't really help me work out how the encryption works still, because it wouldn't be stored in the main firmware. Basically, I didn't know what the keys were or what the encryption algorithm was yet. I knew what the plain text looked like, though, which was very helpful, but if I didn't, because it's an STM32 MCU, there are a few standard parts of memory which we can use as signatures to check where we are. So byte 3 in a firmware will usually be a hex 20, because that's a pointer into RAM, and byte 7 will usually be 08 as a pointer into flash. Other bytes can be assumed as well. There's some that will go to flash, some that go to RAM. You could work with that, but those are the only two you'd really need for this purpose. If I could work out what the encryption algorithm was, I'd be able to use this basically as a comparison or to use do a known plain text attack. So I decided to go through different encryption algorithms on this and upload the firmware with slight modifications. So if it was a stream cipher, as we know, if I changed 1 byte, only that byte in the deployed firmware would change, but it wasn't. If I changed 1 byte in the firmware and the first 16 or 32 bytes were different, then I'd know that it was an ACB mode block cipher, probably AES, but again, it wasn't. If I changed the second block and the first block stayed the same, but the subsequent ones didn't, then they would all change afterwards, but the first one would stay the same. Now, this is where it got interesting, because none of these seem to be the case. So it wasn't a standard encryption algorithm. It was actually using XXT, which some of you may have heard of, but it's a very relatively unknown encryption algorithm. What this one does is you basically give it a huge block, and the block cipher will modify itself depending on how big the block is. So I gave it 512 bytes, and if I changed 1 bit in that, the whole firmware payload would change. I basically took that knowledge and the assumption that it was definitely XXT encryption and went through that entire RAM dump that I got from the start and trying to find any headers that looked similar to what I wanted for a firmware. As I found, the first hit I got was the correct one, providing me with the encryption keys I needed. I then could use that to encrypt the entire firmware dump as needed with these keys, and that's exactly what I needed. 4 32-bit values were the key for this device, allowing me to decrypt and encrypt any firmware. Now, one of the things that you'd want to do with this is dump the bootloader from the device. Now, this would be important for if I bricked it during development, if I wanted to return it back to something normal afterwards, or if I just want to see if it had any other interesting features that I didn't have. I could basically modify the firmware I had in order to add extra functionality in order to modify this, and overwrite the firmware's reset vector in order to make it run my shellcode right at the start. So here's my shellcode, nice and simple. First thing it does is load AABB into the start of RAM on the chip. Now, this makes it very simple for me to know that the code actually ran when I deployed the firmware, and nice and simple. I then made it loop through the entire first hex 4000 bytes of the flash and dump it into RAM. And this basically just dumped the entire bootloader for me to mess with. And I made it infinite loop so it didn't do anything weird with the RAM afterwards. This provided me with, this is a decrypted firmware that I got from the encrypted version. And I found that the reset vector was at hex 100 because it was defined at the top of the firmware in the reset vector. And I just overwrote that with my own shellcode in order to make it do what I wanted. From that, I got the BBAI I expected and the entire contents of the bootloader, giving me access to all the encryption keys for everything, and would allow me to basically deploy anything I wanted to the device or delete it if I wanted to. Basically, knowledge of a firmware update can let you deploy firmware without hardware modification. I wouldn't need to use SWD anymore. I could deploy firmware to it and provide it to people who had bought this device in order to upload malicious firmware without them having to do anything except plug this thing into the USB. I also found more encryption keys to SpyFlash, and I could modify existing parts of the original firmwares in order to do things I wanted. Like if I wanted to make it act like a CAN interface until I wanted to do something nefarious, I could now do this. This was an unsuitable device, which looked similar. Obviously, it's got similar functionality. It's got some buttons and screen. And this is a satellite finder device that I also found online. Had a color LCD, a USB port, and firmware update tools I could use to assess what was going on. But the hardware just wasn't right. So as you can see, the chips look fairly similar to what we saw before in the CAN interface, but then weren't quite because of this particular chip. Now, this is a USB to UART adapter, and basically this is, I'm lazy, I can't be bothered to implement USB on a device, so I stuck a chip on there instead, making it cost more but have less development time. What this means is it can only emulate a serial device now and nothing else. I found the generic tools were used and the firmware updates were unencrypted, because, even though it was using similar chipsets to the originals, which just meant it wasn't as fun to work with either. It also meant that it was using the standard bootloader of the device, meaning it wouldn't have anything for me to exfiltrate even if the chip was locked, which it wasn't. It was using the GD32 MCU chipset, which is a clone of the STM32. It had USB connectivity, but only on the serial chip. It had some LCD screen drivers, but they would have taken up a lot of space if I wanted to deploy anything to it and add my own functionality. And it ran on 9 volts, which was annoying for if I wanted to run it directly off USB. Also, there was no SWD header on it, which has made it not fun at all. This device is somewhat similar. This is an STM32 chip again. This is a 2.4 gigahertz multi-adapter for quadcopters, helicopters, for RF enthusiasts. It has USB connectivity built onto the board, has some switches, and it's quite a neat little device for working with. It's got 4 2.4 gigahertz radios in it, including 1 Chinese one, a Texas Instruments, and a couple of others. Now, being able to access these via the SPI interface on the device would give you quite strong functionality to monitor and transmit on lots of different 2.4 gigahertz frequencies, even at the same time. Now, the internals were quite interesting. It was very, very similar as before, except a few more switches and LEDs. It had a UART header instead of an SWD header, and no facilities for SWD. It did have a bootloader interface and an SPI interface, which I could work with to do some debugging. And what that meant was, instead of basically going through the UART route, the SWD route, I could debug it via UART. Meaning that I wouldn't be able to step through code or do any proper debugging, but I could print out exactly what I needed to. I could deploy any firmwares I had to it and restore firmwares I had already, but it wouldn't really be useful for proper debugging, stepping, or anything else, so I'd have to be very clever about how I did any transmission. I could transmit debugging information over UART, but that's about it. So those are some unsuitable devices. Let's talk about a different project now. So I'm going to talk about CVE first. Now, it's not mine, but it's quite an exciting one. It's CVE 2017-18347. This is a vulnerability in the readout protection of STM32F0 chips, which is a different chipset to which I had originally, but it is a race condition on the chip itself, which basically, when it starts up, when you request firmware from it, if you ask quickly enough, it will give you the firmware. So I wanted to make a device to do that automatically. It's quite a complex thing to pull off. The reason no one found it for a number of years is because SWD debuggers usually go through a whole process of reading IDs, setting up, checking registers before starting. What you need to do is implement SWD and basically get an ID and then read data very, very quickly from the device. So I decided to take a cheap third-party SWD program I had, just as important, ST-Link, from Wingoneer, who I've not heard of before, and delete all the firmware from it and basically turn it from an SWD debugger into an SWD attack tool. So I found another SWC header, as I always do, and deleted all the flash from it, and traced through the resistor ladders that I saw on there to find what each pin on the output was doing, allowing me to basically set up GPIO on the device. And then I implemented SWD from scratch, which is a much simpler task than you think it is. So it's a two-wire protocol usually. It has a clock and a data line. You request data from it, and it gives you it. You write to registers, you read from registers, and that's all you require for communication. Some things have reset pins, some have other weird things, some have like other clocks, inputs, outputs, but not much. But the protocol itself can be bit-banged using just 2 GPIOs on a pin. You send SWD messages by setting the IO to an output, send the message, turn around on a clock cycle in order to make the input and output an input, and then read the data from it or write the data to it, depending on what's going on. This will allow you to read ID codes, write memory, and basically do everything you needed, basically for raw SWD access. I then implemented USB serial on the device, which was very simple, literally just copy and pasting it from the libraries and linking it up as I needed. And I did 2 commands to it. The first being I, which constantly polled for ID codes from the chip, basically identifies that I was actually speaking to something, and D, which dumped firmware from the chip using this exploit, basically powering the thing on and off, constantly going, please give me the firmware, please give me the firmware, and every so often getting a little bit. Now, this will allow you to eventually get the firmware after a number of hours. So yeah, you get the ID codes, and then you can dump the firmware, and this can be a quick demo now. So this is a device plugged into just a raw chip on a board, because I couldn't find a better demo to use, but this is a chip that I've locked the flash on, and I'll show you, this is the thing being powered on. The LED is literally connected to the power and ground pins. The thing found an ID code and stopped, and then it started dumping the firmware. And then on the computer side, I typed in I to start dumping IDs and finding none until I connected up the pin. Got an ID code. And then started dumping flash off the chip, bypassing the readout protection completely. So that's quite fun, but I want to go back to the ODB2 reader now. So obviously, we turned it into a USB hacking device. Now we're going to talk about hardware modifications that could be made to it in order to make it do completely different things that it was intended to. I mean, things that the hardware just doesn't support. There are a bunch of pins on here which I didn't need, so I didn't want to work with CAN at all. So I decided that I could take some of the pins off this in order to make them do something different. I had a look at where the pins were located, got the interrupts and the timers, and replace the CAN pins with these pin setups. And this is enough, as I found out recently, to communicate on NFC, as long as we had a small amount of extra hardware. So at DEF CON this year, on the main stage, I did a talk about making homemade NFC devices. Everything here you can see is basically capable of emulating a MIFARE Classic tag in its entirety with extremely simple components. So we have the ATtiny versions, an STM32 version, and of course the Sonic Screwdriver version. I know, brilliant. At least you guys laughed. What I did was I removed the CAN chips and some of the resistors from the board, and instead soldered wires in their place very carefully in order to basically give me access to these pins to make hardware modifications. I created a small daughter board, which is just about 4 or 5 components, which basically is all you need to convert NFC communication into digital communication, and then solder it onto the board very simply and carefully. On top of this, I basically copied and pasted the code over. Because it was using a 72 megahertz clock speed and all my other devices using the same clock speed, a lot of the code was very much interchangeable. I could add the LCD screen to leverage menu options to the device, basically tag mode, disk mode, NFC mode as needed, which would give me these options. And I implemented mass storage so I could put NFC tag data on the device via USB and then use it as an NFC tag. I basically set up the options as before, taped a massive battery to the back and a coil of wire, and then had a fully working NFC emulation device based on a handful of components. Now, one of the problems I had was disabling STM32's USB stack after it started is a very dangerous thing. It can crash the device, so I decided to crash it myself instead, just to cut out the middleman. There was very little memory left on the thing. It uses 20K of memory, but the NFC stack, mass storage stack, and the FAT32 file system stacks used huge amounts of data. So I had to put the FAT32 file system libraries I had into tiny mode, which is usually for much, much, much smaller chips. But for this, it was absolutely perfect to fill in exactly what I needed and didn't really have any problems, didn't cause me any issues. This is my final demonstration of me emulating an NFC tag using my NFC reader, and hopefully you can spot the red LED flashing to say that it's communicating. And that's the end. Thank you very much. I think we have time for questions, don't we? Perfect. If anyone has any questions. That means I covered everything. Brilliant. Thank you very much.